Here are three different classes of redox reactions. The first one is called combination, and its general form is two things like X and Y will come together and form a single compound, which I'm calling Z. So examples of that are potassium and chlorine forming KCl. So this is one example of a combination reaction would be compound formation reactions. Another example would be nitrogen and oxygen forming NO. So those are combination, two things joined together. The second type would be decomposition, which is just the opposite. One compound falls apart into others. It may be more than two, but it falls apart. So examples of that would be water forming its elements, hydrogen and oxygen. Another one is the ammonium dichromate reaction, which we have seen before. Okay, there's ammonium dichromate, and with a little bit of heat, it breaks apart into chromium 3 oxide and water and nitrogen gas. So this is a single compound that falls apart into some other pieces. The third category is called displacement, and this is where you have a compound, which I'm calling YZ, and something else comes along, X, and replaces Y. So then you have XZ, and then Y is by itself. So it's kind of like there's a couple and someone comes along and steals away Z. Z is so attractive that X steals Z and Y is left all by his or herself. Alright, so an example of that would be zinc plus copper sulfate. The zinc comes along and it bonds with the sulfate, or it becomes oxidized, and the copper becomes reduced from its 2+ state and becomes just copper metal, and this is something we see in a copper to copper lab where we have copper sulfate, which is a blue solution. We put zinc in it, and the zinc replaces or displaces the copper, and you get copper metal out. And in solution you have zinc sulfate. All right, and an activity series is an example of displacement type reactions where you have a list of what can displace what. So the zinc can displace the copper, but the copper is not going to displace the zinc. It's going to go one way or the other. So either it goes this way or it goes this way, and in this case it goes the forward direction. So copper is not active enough to displace the zinc, but zinc is active enough to displace the copper. So we can rank elements according to their ability to displace one another. So an activity list is a list of metals in order of their ability to displace. So for example, in this one up here, we would put zinc above copper. And you could rank a whole list of metals according to their ability to displace. All right, so you could have a general form of, I'll say X, some solid, plus Y. In this case, I'll do a nitrate. And we get X displacing the Y, and Y becomes a neutral species. Okay, so since X displaced the Y, then we can say that X is above Y on the list. And we could do another compound which we could call Q, and if Q could displace the X, then it would go higher than Q. But if it could only displace the Y but not the X, it would go in between. And if it could displace neither, then it would go at the bottom. So you can rank metals this way according to their ability to displace. Okay, redox reactions are balanced by a method known as the half reaction method. And this is where we have a redox reaction which has ionic forms, which we call a skeleton reaction. And here's an example of one. And sometimes you get a skeleton reaction and you need to balance it, and it's a little different process than balancing for neutral entire molecular species. So I will show you the process for balancing a redox reaction with the half reaction method. All right, so you start with your skeleton reaction, which is not balanced at all. Then the first thing you do is you divide it into two half reactions, one that's oxidation, one that's reduction. So you'll have to put the chromium compounds into one, and then we'll put the iodine one into another. So we have an iodine minus going to diatomic iodine. So that's dividing into two half reactions. You could identify which is oxidation and which is reduction, but it's not necessary that you do. All right, the next step is that you balance atoms that are not oxygen or hydrogen. All right, and here we have, so we're not going to balance the oxygen yet, but chromium, we have 2 there, we have 1 there, so we're going to make it Cr2O7 2 minus going to 2 chromium 3 plus, and over here we need 2 I minuses going to iodine. Next step is you balance oxygens using water. Over here we have 7 oxygens. So we need to put 7 waters on the other side. This other reaction does not need to be changed because there's no oxygens that need balancing. So we can kind of draw a little line down here to keep them separate. All right, then balance hydrogens, which you just created, by the way, with acid, H+. All right, so you have 7 waters, which means 14 total hydrogens. So we'll say Cr2O7 2 minus plus 14 H pluses. And the other side stays the same. And we don't have to do anything with iodine. There's no hydrogens to balance. All right, and then you look at the charges and you balance any discrepancy of charges with electrons. Balance with electrons. All right, let's look at this. We have 2 minus charge here, 2 minus there. Here we have 14 H pluses, so we have 14 plus on this side, which means on this side we have, overall, we have 12 plus. On this side we have 3 plus and we have 2 of them, so we have 6 plus. All right, in order to balance with electrons, we'll have to add it to this side because this is more positive, and we're going to need to add 6 electrons in order to make it equal to the 6 plus here, to take 12 plus down to 6 plus. All right, so we'll rewrite Cr2O7 2 minus plus 14H plus, and we'll have to add 6 electrons on that side because we had too many positives on that side. The other side stays the same. Oops. 3 plus 7 waters. Now over here we finally have to do something. We have to balance charges with electrons. We have 2 negative charges in this side, so to balance with electrons we need 2 electrons on the other side. So this becomes 2I minus going to I2 plus 2 electrons. Now our 2 half reactions have different numbers of electrons, so we cannot combine them. We have to multiply by integers to balance the electrons between the 2 half reactions. 6 electrons here, 2 here. We can multiply this one by 3. So we multiply the whole reaction by 3, which means that this reaction becomes 6I minus going to 3I2 plus 6 electrons. It now has 6 electrons like this one does, so we can finally combine our 2 half reactions. Once they have the same number of electrons, we can combine them into one complete full reaction, which I will try to fit here. Cr2O7 2 minus plus 14H plus 6 electrons. Put all the reactants on one side. And so we have a reactant over here, plus 6I minus, and all the products on the other side. 2Cr3 plus 7 waters plus 3I2 plus 6 electrons. Okay, we can cross out anything that appears on both sides. Cross out the 6 electrons, and then we can write what is left. We cancel things. Okay, Cr2O7 2 minus plus 14H plus 6I minus, go to 2Cr3 plus 7 waters plus 3I2, and we are now balanced. Alright, it's a long process, but with practice you can do it yourself. So, follow the steps from the last one and try to do this one yourself. Please stop the video and practice it using the steps I just outlined for you. Alright, I'm going to do it now. I'm going to first divide it into 2 half reactions. The one with manganese will be 1 half reaction. So we'll just write the 2 species. And then the iodine part is the other half reaction. Next step, you balance things other than oxygen. Manganese balanced, iodine's balanced, we're fine. Then you balance oxygens using waters. Okay, this has 4 and 4, doesn't need anything, but this side does. So we make it I minus plus 3 waters, because we need 3 oxygens, goes to IO3 minus. Alright, we don't need anything here, but we need to now balance the hydrogens using H+. So we'll need them on the other side. I minus plus 3 waters give you iodate plus 6 H+. Alright, we are balanced in all atoms. Now we need to balance charges using electrons. On the manganese side, we have just one. We have two minus on this side, 1 minus on this side, so we need an extra electron on the left. Now it's 2 minus on both sides. This reaction has a -1 charge on this side from the iodide, and it has a +6 minus 1 on this side, which is a +5. So on this side we have -1, this side we had +5. To balance those with electrons, we need the electrons on the right side, we need 6 of them. So I'm just going to write a +6 electrons here and cross these out. They were just for noting how much balance we have. Alright, so we have a +6 electrons on the product side here. When you do these types of balancing, you'll always have the electrons added to one side of one of them and the other side of the other. And this is where you can easily see which one's oxidizing, which one's reducing. Because if this is gaining an electron, it is reducing. And if it is losing electrons, it is oxidizing. Okay, we have 1 electron here, 6 electrons here. Now we need to multiply by 6 this whole equation in order to get 6 electrons. So we have 6 MnO4 minus plus 6 electrons going to 6 MnO4 2 minus. Now we have 6 electrons on both. We can combine them, put all the reactants on one side and all the products on another. And we get 6 MnO4 minus. I will leave the electrons out this time. There's all the reactants and the products. 6 MnO4 2 minus plus iodate plus 6H plus. And there is our balanced reaction. Okay, now sometimes, notice that this is in acid. And sometimes we want to balance the reaction in a basic solution. Okay, so if the solution is basic, we have to do one more step. And that step is that we balance the H pluses with OH minus, which is basic. Okay, so we take this reaction and we have to balance the H pluses. We have 6 H pluses. Okay, so we need 6 OH minuses added to both sides. Okay, so let's do that. I will rewrite it. 6MnO4 minus plus iodide plus 3H2O plus 6OH minus plus nothing. Okay. Goes to, whoops, okay. Forget the plus. It's not there. Goes to 6MnO4 2 minus plus IO3 minus plus 6H plus 6OH minus. Okay, now when you have 6H plus and 6OH minus, they combine. That's neutralization. You get 6 waters. And over here, you have 6 OH minuses. You have 6 OH minuses. Okay, so now you've combined those to make water. You have 3 waters over here and 6 waters over here. You can cancel out 3 waters to make that a 3. So now in the end, you will have 3 waters on the product side. Oops, I went too far. So we can rewrite the reaction finally in a basic solution. Okay, and there you have it. Finally, our last topic is going to be redox titrations. Okay, it's similar to an acid-base titration. In an acid-base titration, you may remember that an acid plus a base made water plus something else. And you used an indicator, which is simply a species that changes color. With acidity change. Okay, so you had a visual idea when things changed because of the color change. Okay, well we can do a redox titration where instead of an acid and a base reacting, we have an oxidizing agent and a reducing agent reacting to form some kind of products. Okay, and we have to have a way to tell when we've reached our endpoint. And we often do this with certain species that change color. One example is one that we just used in our balancing is permanganate, which is purple. And so if your oxidizing agent, which is purple, changes to not purple, that's a color change. Another species that can be used is iodine, which is blue in the presence of starch. So you can use the absence or presence of blue to tell when iodine has changed oxidation states. All right, so in this, in permanganate, the oxidation number of the manganese is +7. And so if your product has some manganese 2+, which is a +2 oxidation number, that would be a change. The iodine is 0 for I2. Oxidation number is 0 for I2. And if you change it to iodide, that's a -1. So that would be a change and cause a color change. All right, so what's an example? We'll choose an example that uses permanganate. So we have this reaction, which includes permanganate, and it's a balanced reaction. So you're going to have a reactant that is purple. Okay, this reactant is purple, and you're going to add it drop by drop to this species, which is going to, while this is still the limiting reactant, you won't see any color because it'll immediately turn into Mn2+, manganese 2+, which is colorless. But as soon as you have reached the end point where you have just the right ratio of this permanganate species to this species, then you will one drop over and you will see purple. Okay, so that's basically what you say. One excess drop and it will change to purple. So you can do things like that and do titrations. Of course, in this case, you have a coefficient of 2 and a coefficient of 5. It's not a 1-to-1 coefficient as it often is for acid-base titrations. It's a 2-to-5 ratio. But you can still do titrations and have color changes with redox reactions.